very good day to all of you. Okay, today we are going to learn the line integral of scalar field. Before that, recall back what we have learned in calculus of single variable. We have the integral integral fx dx from a to b. This actually represent the area below the curve y equal to fx, and the x-axis and bounded from x equal to a and x equal to b. The single integral here, integral of fx dx from a to b, actually represent the area below the curve y equal to fx and bounded by x-axis and x equal to a up to x equal to b. In double integral, you have also learned that actually the double integral dA over the region R actually represent the area of this region R. Where the dA in Cartesian coordinate, you can use dy dx or dx dy, or in polar coordinate, you can change it to r dr d theta. If the integrand here no longer 1, but is a function of fxy, and if let's say the fxy represent the surface z, then this integral, this double integral represent if the fxy here represent the surface z, first this double integral represent the volume, bounded by top surface is z equal to fxy, and bottom surface is z equal to 0, where its projection is on region R. And you have this region R is area, and then in the bottom surface is on the region R is the area multiplied by the height, because this is z, multiplied by a height z, once you get the volume like this. You have the surface z, and then on the xy top surface is z, bottom surface is on z0 or xy plane, and when you press your space z parallel with z axis, you get the region R on xy plane. Region R on xy plane is the area times the height, you get the volume of the surface z, equal to fxy bounded on xy plane. If the fxy here represents the density function of a non-homogeneous lamina is actually a very thin sheet, consists of area only. Hence, this double integral represents the mass of lamina in 2D. Because lamina don't have volume, only have the area. If the lamina have a constant density rho, then the mass will be the density times the area. However, the density in the lamina here is non-homogeneous. That's why it becomes the double integral fxy dA over the region R. So if the fxy here represent density function, this is represent the mass of lamina in 2 dimensions. And you have also learned the triple integral. Triple integral 1 dV over the solid G represent the volume of that solid G. If the integrand here is fxyz, which represent the density function, this represent the mass of solid G, because mass is a density function times the volume. However, this is a constant density, but here is a non-homogeneous density functions. Now what we are going to learn here, the line integral. Line integral, the integral ds across the curve C. This represents the total length of curve C. If the integrand is fxyz represent the mass of represent the density function, then this represents the mass of a thin wire curve C. Because thin wire doesn't have area, doesn't have volume, only have the length. So the density function will be, the mass will be density function times the length. However, this is for a constant density. If we have a non-constant density, non-homogeneous density, then the mass of thin wire will be given by the line integral fxyz ds along the curve C. Okay, here we skip, then okay, we'll review back. Okay, what is the meaning of mass of wire in 3 space as line integral? Okay, consider a wire in the 3 space that is sufficiently thin, very thin, that it can be represented by a curve C, where the C is given by parametric equation x equal to xt, y equal to yt, and z equal to zt, or we can put it into the vector value function. Put the parametric equation in the vector form. Mean the curve C represented by the RT, which is xti plus ytj plus ztk. Mean from component I, okay, this one you let it equal to x back. So this x equal to xt, component j, this is equal to y. So y equal to yt, component k, you let it equal to z, hence z equal to zt. And the t is actually in the interval a to b. Okay, mass of lamina, okay, mass of a homogeneous wire, thin wire, is actually the m is a mass, density function find the, okay, this s is the total length. Okay, if we have a mass of a inhomogeneous wire means the density function is not constant but is a function of x, y, z. Okay, then so you have the rho xi, yi, zi times the delta si, where the delta si here is actually one small unit of the arc length in through space. Okay, this is a delta si. And then we can approximate the arc length of delta si, okay, by using Pythagoras theorem, where the horizontal length is delta xi, delta yi is a vertical length, and then we approximate the delta si using Pythagoras theorem, which is a square root delta xi squared plus delta yi squared. Okay, and then if we multiply by delta xi, we have to divide. We have to divide by delta xi. Okay, the division here when go into the square root, it becomes divide delta ti squared. Okay, that's why this is a one small arc length. Okay, so we get this one. And then if we sum up all the small arc length from 1 to n, and actually n approaches infinity, then this will approximate the arc length. So this is the arc length. When the summation is actually, we have the integral of t from a to b. So this is delta xi divided delta ti is the dx dt. Okay, so this squared delta yi divided delta ti, this is dy dt squared dt. This is in 2D. If 3D, it add up one more term here, dz dt squared. Okay, that's why here just now here. So when you sum out each density function delta rho, the function of xi, yi, zi multiplied with delta si, where this is the small units of arc length. Okay, we sum out from 1 to n, where the n approaches infinity. This will approximate to the integral of delta x, y, z ds along the curve C. That's why this is what we call the line integral of scalar field. Okay, if your functions here, there's the integrand here represents density function. This line integral of scalar field represents the mass of a thin wire in 3D space. Okay, if the density function is only xy, then this is a mass of thin wire in 2D space. Okay, and then how to evaluating the line integral of 3D space. So this is the line integral of 3D space, integral of fxyz ds along curve C. Along curve C. You integrate along dx, or along dA, along dV. Now line integral of scalar field. You integrate ds. S is small case, that stands for the arc length. ds is one small unit of the arc length of your thin wire of curve C. Where C is a smooth curve defined by parametric equation x equal xt, y equal yt, z equal zt, or in the vector value function, rt is xti plus ytj plus ztk, where the t from A to B. Then the integral, the line integral of fxyz ds along curve C. To evaluate it, x, variable x is replaced by parametric equation of xt, y by yt, z by zt, ds by square root dx dt squared plus dy dt squared plus dz dt squared outside of the square root dt. Mean the line integral of scalar field is actually you change everything in terms of parameter t and you integrate respect to t, where t from A to B. The square root scale dx dt squared, dy dt squared, dz dt squared is actually equivalent to magnitude r prime t. So the remark, when the fxyz is density function, hence the line integral of scalar field, line integral of fxyz ds along curve C is a mass of a wire in 3 space. If we have fxy only, then it's a mass of wire in 2 space, 2D. When fxyz equal to 1, if this is only 1, so means this is 1, this represents the arc length, the total length of the curve C. Example 1, find the mass, the mass of a thin wire, given by x equal to cos t, y equal to sin t, z equal to 2t, where the t from 0 to pi, if the density function rho xyz is equal to kz. Once the mass, you have the density functions, find the ds, ds. Remember your mass, you have the integral of your density function rho x, y, z multiply ds as lowercase along the curve C. Ds is actually square root dx dt squared plus dy dt squared plus dz dt squared dt. Rho xyz given is k times z. So plug in. This is k z. Z, what is z here? Z is 2t. So the density function k times z. So k and then z we have 2. So 2kt. So this will have 2kt. Square root of dx dt squared. X is cos t. Dx dt you have negative sin t. So negative sin t squared. Dy dt. Dy dt you have cos t. So cos t squared. Dz dt is 2. So plus 2 squared. And then sin squared t plus cos squared t is 1. So here 1 plus 4, you have a third 5 here. So this one evaluates your dx dt squared plus dy dt squared plus dz dt squared. You get the answer is, here total is third 5. Third 5 is factor out. So it's just left integral of t dt. So I have t squared over 2, plug in the upper limit, it's 2 and 2 cancel. So I have third 5k I squared. So this is the mass of the thin wire. Example 2, evaluates the line integral of scalar field, integral of x plus 2 ds along curve C, where C is a curve represented by rt equal to ti plus 4 over 3 t power 3 over 2j plus half t squared k, where the t from 0 to 2. Okay, remember just now we said we have two ways to present the curve C. It's either is given in the parametric equation x equal xt, y equal yt, z equal to zt, or given into the vector value function rt is xti plus ytj plus ztk. And then from the component I is actually is x equation, meaning let it equal to x, component j let it equal to y, component k let it equal to z. You can identify your x, y, z, and and the ds is square root dx dt squared plus dy dt squared plus dz dt squared, or is actually magnitude r prime t. Magnitude r prime t. Once here rt is ti plus 4 over 3 t power 3 over 2 j plus half t squared. R prime t means you ddt the rt, ddt t you have 1i, ddt 4 over 3 t power 3 over 2, so you get left 2t power half j, then ddt half t squared, you have t k. So you find magnitude, mean the ds also equal to the magnitude r prime t. To find magnitude of a vector, have a big square root. Each component you square it. So 1 is 1i, so 1 squared you have 1. 2t power half you square it, so you have 4t. Component k is t, so you square it tk. So hence the line integral of x plus 2 ds along curve C, where the t from 0 to 2, t from 0 to 2, so x plus 2. From r here, component I, this is actually x. So replace x by t, so t plus 2. ds is actually magnitude r prime t, so magnitude 1 plus 4t plus t squared. 1 plus 4t plus t squared. Then, where is the thing that I have? And then, to evaluate this integral, you use a substitution technique. Hold on, let me see. This one. Oh, here. This one. To evaluate this integral, mean the x from here x is t, integrate from 0 to 2, ds is magnitude, magnitude square root 1 plus 4t plus t squared, and to evaluate this integral, you may use substitution technique, u equal to 1 plus 4t plus t squared. 1 plus 4t plus t squared, and then so your du, because you want to you want dt, so du dt will be 4t plus 2t. So du dt is 4 plus 2t, so this 4 plus 2t dt. With du dt, you have 4 plus 2t, so du will be 4 plus 2t dt. You notice that you want dt only, dt. So you want t plus 2, dt. So t plus 2 dt will be du over 2. You want t plus 2 dt. You want t plus 2 dt will be du over 2. Hence the integral t plus 2 square root 1 plus 4t plus t squared dt, where the t plus 2 dt you replace by du over 2, and then the square root 1 plus 4t plus t squared is a u power half, because you have denote u is 1 plus 4t plus t squared. So integrate u, half of u power half, you get half of u power 3 over 2 divided by 3 over 2. So 2 and 2 here cancel. So you get u power 3 over 2 divided by 3. Replace back the u is actually 1 plus 4t plus t squared. So you have 3 power 3 over 2 divided by 3 here. Then evaluate it from 0 to 2. Okay. So put in here 2. So total you have 1 plus this is 8. 2 squared you have 4. So total you have here, okay, 1/3 is actually 13 power 3 over 2. Okay, and then when you plug in 0, you have actually 1. 0 here, 0 here, 1 power 3 over 2, you get 1. Okay, and then this is 13 at 1/3. 13 power 3 over 2 is actually you have sub 13 power 3. Sub 13 power 3 where you get back, okay, sub 13 times sub 13 is 13, so you have one more sub 13. Okay, that's right, your answer. You have 13 sub 13 minus 1 divided by 3. Okay, and then I'm not sure whether you can try to use your scientific calculator to, okay, finding my scientific calculator. Okay, you can have a try. This integral using your scientific calculator. Okay, of course, scientific calculator, the integral, the t, you have to change it to x. So integrate, let's say, x is the red color, need to press the alpha, so alpha x plus 2. Have the square roots, 1 plus 4 alpha x plus alpha x squared. Okay, evaluate from 0 to 2. Okay, 15.2907. Okay, using the calculator, okay, so you have to check whether this value, let me check that, this value here, this value, 2907. 2907. Okay, let me check whether equal, okay, to what we obtained manually. 13 sub 13 minus 1 divided by 3. Yeah, same. So means K, in case K, you forgot how to integrate it, and luckily this is the finite integral. Okay, you may use your scientific calculator to integrate it. Of course, the scientific calculator, the integral is in terms of x. So all the t here, you have to change it to x. But here, okay, we should show you both ways, okay. Either using, okay, scientific calculator or you use substitution techniques. So we, okay, concludes back what we have learned in the line integral of scalar field. Okay, line integral of scalar field. Okay, conclude back what we have learned. Okay. Okay, this is line integral of scalar field in 3 dimensions. We give you 3 dimensions. If only 2 dimensions, you don't have the variable z. If the f, x, y, z represent density function, this line integral of scalar field represent the mass of a thin wire in 3D space. 3D space. And then how to evaluate this line integral? Okay, the curve C may be given in the parametric equation x equal xt, y equal yt, z equal zt, or in the vector value function. which is rt equal to xti plus ytj plus ztk, where the t in the interval a to b. Then to evaluate the line integral of scalar field, you replace all the x, y, z in their parametric equation xt, yt, zt. ds is actually square root of dx dt squared, dy dt squared, dz dt squared, dt. So integrate everything in terms of t respect to dt from a to b. Okay, if the parametric equation is given in the vector value function rt, the ds also can be evaluated using the magnitude r prime t dt. Then as I said, if the fx, y, z represent density function, this represents the mass of wire in 3 space. If fx, y, z equal to 1, this is the length or total length of the curve C. And so with this, thank you for your attention and watching this video.